Something is wrong at the edge of our solar system. Not wrong in a subtle way. Not wrong in a way that takes years of squinting at data to notice. Wrong in a way that has forced some of the most careful planetary scientists alive to sit down, run the numbers twice, and then admit that something out there is pulling on things it should not be able to reach. Objects so far from the sun that sunlight reaching them is barely a whisper. Objects taking thousands of years just to complete a single orbit. Those objects are not behaving the way they should. Their paths through space are clustered, aligned, pointing in the same direction, as if something enormous is standing just out of sight and tugging. No known planet can do this. Neptune, the farthest confirmed world in our solar system, is not anywhere close to far enough out. Whatever is causing this is deeper in the dark than anything we have ever named. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Here is the scale of what we are talking about. Earth orbits the Sun at roughly 93 million miles out. Astronomers use that distance as a unit of measurement, 1 astronomical unit. Neptune sits about 30 of those units out, already unimaginably remote. The objects at the center of this mystery orbit at distances of 250, 500, even beyond 1,000 astronomical units from the Sun. These are not planets. They are small, icy bodies left over from the formation of the solar system, drifting through a region so distant and so cold that the Sun looks like nothing more than a bright star from their surface. They should be scattered randomly. Nothing should be organizing them. And yet, when researchers mapped their orbits, they were not random at all. The idea that something is out there goes back further than most people realize. But the modern version of this story begins in earnest around 2014, when 2 astronomers noticed that a handful of these distant, icy objects shared an orbital property that had no business being shared. The odds of this happening by chance were tiny, not impossible, but small enough to demand an explanation. That observation started a chain of events that ended with a formal scientific paper, published in 2016, proposing that a planet roughly 5 to 10 times the mass of Earth is orbiting our Sun right now at a distance hundreds of times greater than Earth's. The paper named it Planet 9, and it came from 2 of the most credentialed planetary astronomers working today. This is not a fringe claim from someone posting to a forum at midnight. Mike Brown is the astronomer at Caltech who discovered so many large objects in the outer solar system that the scientific community was eventually forced to demote Pluto from planetary status. He is, in a real sense, the person most responsible for the solar system having 8 official planets instead of 9. His collaborator, Konstantin Batygin, is a theoretical physicist and planetary scientist whose entire job is building mathematical models of how planets form and evolve. When these 2 say that the evidence points toward an undiscovered planet, the community listens. Not everyone agrees, but no one dismisses it. What makes this genuinely unsettling is that the evidence has not gone away. Every year since 2016, new objects have been found in the outer solar system, and many of them fit the predicted pattern. The gravitational fingerprints keep showing up. The clustering keeps holding. Attempts to explain it away with observational bias have not fully worked. The mystery has only gotten more detailed, more specific, and harder to handwave out of existence. Brown himself has said he is extraordinarily confident the planet is real. Other researchers are more cautious, some are skeptical. But the question is alive in a way that legitimate scientific questions are alive, argued over at conferences, tested against new data, refined with every new discovery from the distant solar system. There is also a candidate. In 2025, researchers digging through archival infrared survey images taken 23 years apart found an object that appears to have moved exactly the amount a planet at Planet 9's predicted distance would move. It has not been confirmed. It has not been given a name, but it exists as the best physical lead the search has ever produced. So here is where things stand. Either a significant subset of the most capable planetary scientists alive have been fooled by a statistical ghost for over a decade, or there is a world out there in the dark that nobody has directly seen yet, orbiting our sun on a path so vast it takes between 10 and 20,000 years to complete a single loop. The question is not whether someone invented this story to fill a slow news cycle. The question is whether a world larger than Earth is sitting out there right now, invisible, and we simply haven't looked in the right place yet. Before getting into what the evidence shows, it helps to understand what exactly researchers are talking about when they say Planet 9. Planet 9 is not a confirmed planet. It has not been photographed. No telescope has resolved it as a disk, tracked its motion across the sky, or measured its light. What it is, at this point, is a hypothesis, a predicted object whose existence would explain a set of observations that currently have no better explanation. That distinction matters. When astronomers talk about Planet 9, they are describing something they believe is probably out there based on gravitational evidence, not something they have actually seen. So what do the predictions say? The leading models suggest Planet 9 is somewhere between 5 and 10 times the mass of Earth. That puts it in a category planetary scientists call a super-Earth, or depending on its composition, a mini-Neptune. These are not exotic categories. They are actually the most common type of planet found around other stars in the galaxy. Survey after survey of distant star systems has turned up planets in this size range more often than any other. What makes Planet 9 strange is not what it is where it is. Our solar system, for a long time, appeared to have none of these mid-sized worlds. Every planet here is either small and rocky like Earth, or enormous like Jupiter. There is nothing in between, at least not anywhere close. Planet 9, if it exists, would fill that gap. It would just be doing it from an almost unimaginable distance. To understand how far out we are talking, you need a unit of measurement that makes the solar system navigable. Astronomers use the astronomical unit, abbreviated AU, which is simply the average distance from Earth to the Sun. That number is about 93 million miles, or 150 million kilometers. Neptune, the outermost confirmed planet, orbits at roughly 30 astronomical units. In human terms, light takes about 4 hours to travel from the Sun to Neptune. A spacecraft moving at the speed of the New Horizons probe. That is currently the fastest human-made object heading away from our solar system. Would take roughly 12 years just to reach Neptune from Earth. Planet 9 is predicted to orbit somewhere between 290 and 500 astronomical units from the Sun. The estimates have shifted over time as new data and better models have come in. But even at the lower end of that range, you are looking at a distance nearly 10 times farther than Neptune. Light that left the Sun this morning would take almost 2 days to reach Planet 9 at 400 astronomical units. That same New Horizons spacecraft, traveling at full speed, would need over 70 years to get there. The planet sits in a region of the solar system so remote that sunlight arriving at its surface is roughly 1/1,000,000th the intensity of sunlight on Earth. It would be essentially dark out there. The orbit itself is not circular. Planet 9 is predicted to follow a highly elongated path, swinging from a closest approach of perhaps 200 astronomical units out to a farthest point somewhere beyond 600 astronomical units before looping back in. One complete orbit around the Sun at that distance would take somewhere between 10,000 and 20,000 years. For context, 10,000 years ago, the last ice age was ending. Humans were just beginning to settle into agricultural societies. Every civilization that has ever existed on this planet has risen and fallen within the span of less than one Planet 9 year. The orbital period is so long that in the entire history of recorded observation, the planet would have moved only a tiny fraction of the way around its track. This extreme orbit is part of why nobody has found it yet. A planet that spends most of its time at distances of 400 or 500 astronomical units from the Sun reflects almost no sunlight back toward Earth. It would appear as an extraordinarily faint point of light, moving so slowly against the background stars that distinguishing its motion from noise requires comparing observations taken months or years apart. It is genuinely difficult to find. What researchers do have is a predicted mass range, a predicted orbital region, a predicted inclination, and a predicted distance. Recent models from 2025 have actually tightened the estimates somewhat, pulling the likely orbit a bit closer than earlier calculations suggested, somewhere around 290 to 460 astronomical units, rather than the original 400 to 800. The mass estimate has also come down slightly. Earlier papers favored something closer to 10 Earth masses. More recent work suggests 5 or 6 Earth masses is more likely. Some modeling points toward a composition that is rockier than the ice giant picture that dominated early descriptions of the object. None of these refinements change the fundamental picture. This is still a large world orbiting in the deep dark at a distance that dwarfs anything we have ever directly explored. What makes the hypothesis scientifically serious rather than speculative is precisely what it is not based on. It is not based on a single researcher's calculation or a mathematical anomaly in one dataset. It is based on the orbital behavior of multiple independent objects in the outer solar system, objects whose paths cannot be explained by the gravity of any known planet. The gravitational fingerprint of something massive and distant is showing up across a range of observations made by different teams using different instruments over more than a decade. Whether that fingerprint belongs to a real planet or has some other explanation is still an open question. But the fingerprint itself is not in dispute. Every single thing astronomers currently believe about Planet 9, its mass, its orbit, its distance, even whether it exists at all, has been inferred from the behavior of other objects, none of which have ever been close enough to feel its gravity directly. The search for an undiscovered planet beyond Neptune is not a new idea. It is, in fact, one of the oldest recurring obsessions in modern astronomy. Since Neptune was confirmed in 1846, at least 30 separate researchers have proposed that something larger, something unseen, was hiding even farther out. Every single one of them was eventually proven wrong. That streak matters. It is long enough and consistent enough that the first honest question anyone should ask about Planet 9 is a simple one. Why would this time be any different? To understand why the history is so embarrassing, you have to go back to how Neptune itself was found. That story is one of astronomy's genuine triumphs. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently noticed that Uranus was not moving the way it should. Its orbit had small but measurable wobbles that Newton's laws could not explain if the known planets were all there was. Both men did the math. Both concluded something massive was pulling on Uranus from beyond. Le Verrier sent his predicted coordinates to an observatory in Berlin. They pointed their telescope and found Neptune within an hour. It was one of the most dramatic confirmations in the history of science. That success planted an idea that would haunt astronomy for the next century. If you could predict Neptune from Uranus's wobbles, maybe you could predict something beyond Neptune the same way. And almost immediately, people started trying. By the late 1800s, several astronomers had noticed that Neptune itself seemed to have small irregularities in its orbit. The conclusion felt obvious. There had to be another planet out there, something big, something tugging at Neptune the way Neptune tugged at Uranus. The hunt was on. Nobody pursued it harder than Percival Lowell. He was wealthy, he was determined, and he was almost pathologically convinced that a trans-Neptunian planet existed. He called it Planet X, not because he didn't know what it was, but because X meant unknown. Starting around 1906, Lowell funded an observatory in Arizona specifically to find it. He ran calculations. He produced predicted positions. He searched the sky for years. He found nothing. Lowell died in 1916 without his planet. His observatory kept searching after his death, driven partly by institutional momentum and partly by genuine scientific interest. Then, in 1930, a young assistant at Lowell Observatory named Clyde Tombaugh found something. He was blinking photographic plates, comparing images of the same piece of sky taken on different nights, looking for anything that moved. Something moved. It was faint, slow, and sat almost exactly where Lowell's calculations had suggested Planet X might be. The news spread around the world. Lowell's prediction seemed vindicated. The object was named Pluto, after the Roman god of the underworld, and for a few months, it looked like the long hunt was finally over. It wasn't. Almost immediately, problems appeared. Pluto was too faint. Astronomers tried to calculate its mass from the way it was supposed to be influencing Neptune, and the numbers didn't add up. The more carefully they measured, the smaller Pluto seemed to get. It couldn't be responsible for the orbital wobbles that had motivated the search in the first place. By mid-century, it was clear that Pluto was not Planet X. It was something much smaller, much stranger, and essentially coincidental. The apparent confirmation of Lowell's prediction turned out to be luck. The planet he was actually looking for was never found because it didn't exist, but that realization took a long time to sink in. Through the 1940s, 50s, and 60s, astronomers kept proposing additional planets. The orbital anomalies in Neptune and Uranus kept appearing in different datasets, under different analyses, interpreted in different ways by different researchers. Each new claim attracted attention. Each eventually collapsed. The wobbles turned out to be measurement errors. When Voyager 2 flew past Neptune in 1989 and gave astronomers precise mass measurements for the first time, scientists went back and recalculated Uranus's orbit using the corrected Neptunian mass. The wobbles disappeared entirely. There were no anomalies. There had never been anomalies. The whole foundation of a century of Planet X searching evaporated in a single recalculation. What makes that particularly striking is the sheer number of very capable scientists who had built careers around something that wasn't there. This was not fringe science. Some of the people proposing trans-Neptunian planets were serious researchers at serious institutions working with the best data available to them. The data was just wrong, or incomplete, or being interpreted through assumptions that weren't valid. The pattern repeated itself so many times that by the 1990s, healthy skepticism toward any new Planet X claim was essentially the default position in the field. And that skepticism was earned. So when Batajian and Brown published their paper in 2016, arguing for Planet 9, they were walking into this history. Brown, in particular, knew exactly what it looked like. He had spent years studying the outer solar system and years watching speculative planet claims fall apart. He was not someone prone to wishful thinking about undiscovered worlds. When he and Batajian started working on the clustering problem, Brown's initial job was to find the conventional explanation, to identify the prosaic reason the data looked the way it did, and close the case without invoking anything new. The difference this time, and the reason serious researchers did not immediately file the claim alongside Lowell's notebooks and the corrected Neptune calculations, was the nature of the evidence itself. Every previous Planet X claim started with a theorist noticing a discrepancy and proposing a planet to explain it. The discrepancy always evaporated when the data improved. The Planet 9 claim started differently. It started with actual objects in actual orbits, objects that had been measured carefully and repeatedly, behaving in ways that nobody could explain. No measurement error makes a dozen objects point in the same direction. No instrument calibration issue creates a clustering signal across independent surveys. The track record is brutal, and any honest account of the Planet 9 hypothesis has to start by acknowledging it, because the only thing that makes this time feel different is that for the first time, the evidence is not coming from one person's wishful calculations, but from objects in the actual sky that are doing something nobody can explain. To understand why anyone thinks there is a ninth planet, you have to start with the Kuiper Belt. Most people learn the solar system as 8 planets and then empty space stretching out to infinity. That picture is wrong. Beyond Neptune, starting at roughly 30 astronomical units from the Sun, there is an enormous ring of material. Icy, rocky, cold, and sprawling. It extends outward to somewhere around 50 astronomical units before thinning out. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt begins nearly 3 billion miles out and stretches billions of miles beyond that. Pluto lives there. So do hundreds of thousands of smaller bodies, maybe more. Short-period comets, the ones that swing through the inner solar system on cycles of less than 200 years, almost certainly originate there, knocked inward by gravitational nudges over millions of years. The Kuiper Belt is not chaos. It has structure. The objects inside it follow predictable rules, and the dominant force shaping those rules is Neptune. Neptune's gravity acts like a traffic warden for the outer solar system, shepherding Kuiper Belt objects into stable orbital configurations, pushing some inward, flinging others outward, setting the boundaries of the belt itself. Most Kuiper Belt objects orbit on paths that are relatively flat compared to the plane of the solar system, relatively circular, and never too far from Neptune's influence. When something does get knocked onto a wild, elongated orbit, Neptune's gravity eventually pulls it back into a more settled configuration. The system is messy in the details, but organized in the broad picture. Neptune runs the neighborhood. Then there are the objects that do not fit that picture at all. Scattered deep enough beyond the main belt, you find a population of bodies on orbits so stretched and so distant that Neptune can barely reach them. These are the extreme trans-Neptunian objects, sometimes called ETNOs. Their paths are not circular. They are long ellipses, dramatically elongated, that carry them out to hundreds of astronomical units from the Sun before swinging them back inward. Some reach 500 astronomical units at their farthest point. A few go farther still. At those distances, the Sun's light takes days to arrive. The temperature drops close to absolute zero. These objects spend most of their orbital lives in a region so remote, it barely registers on any map of the solar system most people have ever seen. What makes ETNOs particularly interesting is not just how far they go, it is what governs them when they get there. At 200, 300, 500 astronomical units from the Sun, Neptune's gravitational reach is essentially zero. These objects have sailed far beyond the point where Neptune can do anything meaningful to their orbits. At those distances, the only force that should matter is the gravity of the Sun itself, pulling everything inward on long looping paths. The inner planets, the outer planets, even Jupiter, none of them have meaningful influence at these scales. The Sun dominates, and the Sun is symmetric. It pulls equally in every direction. Here is why that matters. If the Sun's gravity is the only thing shaping the orbits of extreme trans-Neptunian objects, and if the Sun pulls equally in every direction, then the orbits of those extreme objects should point in random directions. There is no reason for them to prefer one orientation over another. Some should be tilted this way, some that way. Their long axes should be scattered across the sky like compass needles with no north. That is what the math says. That is what every model of the outer solar system predicted before anyone looked carefully. What actually showed up in the data was something else entirely. When researchers began cataloguing enough extreme trans-Neptunian objects to look for patterns, they found that the orbits were not scattered randomly. They were bunched. Multiple objects, independently following their own long, lonely paths around the Sun, seemed to be oriented in roughly the same direction. The long axes of their ellipses pointed in a similar region of sky. Their orbital planes tilted in similar ways. The alignment was not perfect, but it is far too consistent to look accidental. And the more objects researchers found, the more the pattern held. Random processes do not produce this. If you flip a coin 50 times and it comes up heads 40 times, you stop assuming the coin is fair. The solar system was flipping the same way over and over. Something was biasing the outcome, organizing these objects, pulling their orbital orientations into rough agreement. And whatever it was not Neptune. Neptune was too close, too weak at these distances, too irrelevant to the extreme objects to be the cause. There was no obvious candidate in the known solar system. Jupiter was too far in. The known planets collectively could not account for it. The Sun, symmetric and indifferent, certainly was not doing it. This is the kind of signal that keeps researchers awake. Not a spectacular explosion, not a dramatic collision, just numbers that do not behave the way numbers are supposed to behave. A quiet, stubborn pattern in the orbital data of objects most people have never heard of. It did not look like noise. It did not look like bias. It looked like something was out there, somewhere beyond the edge of the known solar system, doing exactly what a massive, unseen planet would do. The orbits of the most distant objects in the Kuiper Belt were not scattered randomly across the sky the way they should be. They were clustering, pointing in the same general direction, as if something massive was standing just out of frame and pulling on all of them at once. In 2014, Chad Trujillo and Scott Shepherd published a paper that most people outside astronomy never heard about. It did not make the front page. It did not trend online. A few dozen planetary scientists read it carefully, nodded, and filed it away. But buried inside that paper was a number that did not make sense, and numbers that don't make sense have a way of coming back. Trujillo had spent years doing exactly the kind of work that does not get you famous. Systematic surveys of the outer solar system, pointing telescopes at faint, cold stretches of sky, running image stacking software for hours, looking for objects that barely moved. He had trained under Mike Brown at Caltech, one of the most productive planetary astronomers of his generation. Brown's group had found more distant solar system objects than almost anyone alive. Trujillo absorbed that approach, then took it further on his own. By 2014, he was running a dedicated survey program with Scott Shepherd at the Carnegie Institution, hunting for whatever was hiding in the deep outer solar system. They were not looking for anything in particular. They were looking for everything. Then they found something they were not looking for at all. While compiling a new distant object called 2012 VP113, Trujillo and Shepherd did what careful astronomers always do with a new discovery. They compared it against everything else known in that orbital region. And they noticed something strange. Not just about 2012 VP113, about 13 of the most extreme objects in the entire catalogue. All of them shared a suspicious similarity in an obscure orbital parameter. The same number, clustering around the same value, across 13 separate objects that were supposed to have nothing in common. The odds of that being random chance were extremely small. The parameter in question is called the argument of perihelion. That phrase sounds complicated, but the underlying idea is not. Every object orbiting the Sun has a closest point in its orbit, called perihelion. The argument of perihelion describes the orientation of that closest point relative to the plane of the solar system. Think of it this way. Imagine the solar system as a flat clock face. Every orbit has a point where it swings closest to the center. The argument of perihelion tells you where on that clock face the closest approach happens. For a random collection of objects scattered by ancient gravitational encounters, those closest approach points should be aimed in all different directions. 12 o'clock, 6 o'clock, 3 o'clock, everywhere. No particular direction should dominate. What Trujillo and Shepherd found was that the most extreme objects were not pointing in all different directions. They were clustered. The argument of perihelion values for those 13 objects were all hovering near 0 degrees, not scattered, concentrated. Something was keeping those orbital orientations corralled into the same general region of space, and nothing in the standard model of the solar system could explain it. Here is what makes that finding important. These were not ordinary Kuiper Belt objects sitting just beyond Neptune. These were the most extreme ones, objects with orbits so elongated and so distant that Neptune's gravity barely reaches them. At those distances, Neptune cannot hurt anything. It does not have the gravitational muscle. Whatever was organizing those orbits had to be something else, something farther out, something not yet identified. Or the clustering was a fluke, a statistical ghost in a small sample. Trujillo and Shepard were careful. They did not claim a planet existed. That would have been a significant overreach from 13 data points and one suspicious orbital parameter. What they wrote instead was more measured. They flagged the anomaly, calculated the probability that it was random, concluded the probability was low enough to warrant attention, and suggested that a distant undiscovered body could plausibly explain what they were seeing. Then they published it and let the community decide what to do with it. This is how real scientific discoveries often begin. Not with a dramatic announcement, with a footnote, with a number that sits slightly off from where it should be, and a careful observer who decides to write it down rather than ignore it. The paper moved through the community at the speed of academic correspondence. Some researchers found it interesting but not compelling. 13 objects is a small sample. Small samples can fool you. Others thought the observational bias argument was strong enough to table the whole discussion, since surveys tend to discover objects in places they've looked most, and looked at places are not randomly distributed across the sky. The clustering might be real. It might be an artifact. Without more objects, it was genuinely hard to say. But some people read it differently. Some people looked at that concentration of arguments of perihelion near 0 degrees and thought about what kind of object, at what kind of distance, could produce exactly that pattern. Not as a vague possibility, as a specific, calculable gravitational problem. What mass would be required? What orbit would be required? Whether the numbers could actually work. Those questions take a certain kind of mind to pursue. Someone comfortable with orbital mechanics at scales that make most calculations meaningless. Someone willing to spend months building simulations that might produce nothing. Someone with enough credibility to publish a result that would be scrutinized intensely and enough stubbornness to defend it anyway. The paper landed on the desk of Mike Brown at Caltech, the same astronomer who had killed Pluto's planetary status 9 years earlier. And this time, he brought in a theorist named Konstantin Batygin to figure out what was actually going on. For several months in 2015, Batygin and Brown worked in something close to secrecy. Not because they were trying to scoop anyone, because they were embarrassed by what they were finding. Mike Brown is not someone who believes easily in undiscovered planets. His career had gone almost exactly the opposite direction. He spent years in the early 2000s systematically hunting down objects in the outer solar system and proving that the things people had mistaken for giant unseen worlds were actually just small icy bodies that nobody had catalogued yet. He was, by his own description, the person who killed Pluto. He had made a professional habit of deflating planet rumors. When the Trujillo and Shepard paper crossed his desk in 2014, pointing at that strange clustering in the argument of perihelion, his first instinct was not excitement, it was skepticism. His first instinct was to find out what everyone else was getting wrong. Konstantin Batygin came at the problem from a different angle. He is a theorist, the kind of researcher who builds mathematical models of how gravitational systems evolve over millions of years. Brown brought him in specifically to stress test the clustering signal, to run the numbers and find the conventional explanation that would make the anomaly disappear. That was the plan. That was the assignment. Find the boring answer. They started with the 6 extreme trans-Neptunian objects that had the best characterized orbits. These were not random selections. They were the objects with enough observational data that their orbital parameters could be trusted. The clustering those 6 objects showed was not subtle. Their orbits were not just pointing in roughly the same direction. They were aligned in 3 dimensions, tilted the same way, oriented the same way, behaving almost like they had been arranged deliberately. The probability of that happening by chance was somewhere around 0.007%, roughly 1 in 15,000. Batygin started working through explanations. Maybe the clustering was an artifact of the way the Kuiper belt forms, some kind of structural feature baked into the disk of debris left over from the early solar system. The models said no. Maybe it was the gravitational influence of a passing star early in the solar system's history, something that had left a long fingerprint on the distant debris. Possible in principle, but the geometry was wrong and the timescales didn't hold together. Maybe there was some interaction between these extreme objects themselves, a kind of collective gravitational effect that kept their orbits synchronized. He ran that model. It failed. The objects are too spread out and too light to gravitationally influence each other in any meaningful way. One by one, the conventional explanations broke down. What happened next is the part Brown has described publicly, and with some obvious discomfort. After exhausting the standard options, Batygin ran a simulation with a hypothetical planet sitting on the opposite side of the solar system from the clustered objects, an anti-aligned orbit, a planet whose elongated path pointed roughly away from the 6 extreme TNOs rather than toward them. This is counterintuitive. You might expect a planet to pull things toward it, not away. But orbital mechanics over millions of years don't work the way intuition suggests. Through a process involving mean motion resonances, where objects settle into stable gravitational relationships with each other based on their orbital periods, a planet in this anti-aligned configuration would actually trap the extreme objects and keep their orbits locked in alignment on the opposite side of the sky. When Batygin plugged a planet into that configuration, the simulation reproduced the clustering almost perfectly. Brown looked at the results. He had spent years telling other astronomers they were wrong about outer planets. He had a reputation built on skepticism, and here was his own simulation, telling him the same thing everyone he had dismissed had been saying, that something was out there. He has said since that he found the result genuinely hard to accept, that he checked the math, checked it again, and kept looking for the flaw. There was no flaw. What made Brown eventually willing to say it out loud was not just the simulation, it was Batygin's point about the nature of the prediction. Previous Planet X claims over the decades had a common flaw. They started with a wobble in someone's data, proposed a planet to explain it, and stopped there. the planet was whatever size and distance you needed it to be to make the numbers work. There was no independent test. You couldn't go look somewhere specific and either find it or not. Batigin's model was different in a specific way. It didn't just reproduce the clustering, it specified properties. The planet had to be in a roughly anti-aligned orbit. It had to have a mass somewhere in the range of 5 to 20 Earth masses. It had to have a semi-major axis in the hundreds of astronomical units. The model predicted what it had to be, not just that something had to exist. That specificity is what distinguishes a real scientific hypothesis from a pattern people talk themselves into. Batigin has said that every Planet X proposal before this one was essentially a story. You could adjust the planet's parameters freely until the evidence fit, which means the evidence wasn't actually testing anything. This time, the math locked down the parameters independently. The planet had to fit in a particular region of orbital space, or the whole model broke. That is a prediction you can go test with a telescope. That is a prediction that can be falsified. Brown, for his part, described the experience of switching sides as something between uncomfortable and slightly surreal. That after years of being the one who said these planets don't exist, he was now standing in front of a calculation he couldn't refute. The two wrote it up and submitted it to the Astronomical Journal. When the paper was published in January of 2016, it did not claim a discovery. It claimed a prediction, and the difference matters, because a real prediction can be tested. And that was exactly what the community was about to try to do. The single most important question about the Planet 9 hypothesis is whether the clustering of distant objects is real, or whether it is an artifact of where telescopes happen to have been pointed. When Batigin and Brown published their 2016 paper, they were working with 6 objects. 6 extreme trans-Neptunian objects, whose orbits all seem to be pointing in roughly the same direction. 6 sounds small. It sounds like the kind of number a skeptic could dismiss in an afternoon. But what made these 6 objects remarkable was not just that they were pointing the same way. It was the specific combination of properties they shared. Their orbits were aligned in the same direction, yes. They were also bunched in terms of orbital tilt. And the long axes of their ellipses, the lines that define the orientation of each orbit through space, were clustered together in a way that defied easy explanation. You're not just seeing 6 arrows pointing the same way. You're seeing 6 arrows that are tilted at similar angles, spun to similar orientations, arranged as if something had reached in and organized them. The probability calculations that came out of the 2016 paper were striking. Batigin and Brown estimated the odds of that particular configuration occurring by chance at around 0.007%. That's roughly 1 in 14,000. Other researchers, using somewhat different statistical methods and slightly different object selections, put the number closer to 1%. 1% is not 0, but it is still the kind of number that demands explanation. If you shuffled a deck of cards and the first 6 cards were all aces, you wouldn't assume the deck was fair. Here is what anti-alignment actually means, because it's one of the genuinely counterintuitive things about the whole hypothesis. Planet 9 is not predicted to sit in the same direction as the objects it is influencing. It's predicted to sit on the opposite side of the sky. The clustered objects are bunched in one region of their orbital orientation. Planet 9 is expected to be bunched in the opposite region. This seems backwards at first. If a planet is pulling things toward it, why would the objects end up pointing away from it rather than toward it? The answer comes from orbital mechanics and the timescales involved. Over millions of years, as Planet 9 and these distant objects slowly interact through gravity, the resonant dynamics of the system push the objects into configurations that are anti-aligned with the planet's own orbit. Think of it less like a magnet pulling iron filings toward it, and more like a slow gravitational game where the planet keeps nudging objects into a stable configuration on the far side. The objects aren't pointing toward Planet 9. They're pointing away from it because that is where the long-term stable configuration ends up. It's not intuitive, but the math is solid, and it's one of the features of the hypothesis that couldn't have been guessed without running the actual simulations. Now here is where things get genuinely complicated, because the anti-alignment prediction runs directly into the observational bias problem. Most deep surveys of the outer solar system have been concentrated in specific regions of the sky. The reason is practical. Some regions are easier to observe from particular telescopes. Some regions are darker, further from the galactic plane, less cluttered with background stars. If most of the searches have been conducted in certain patches of sky, then most of the objects found are going to be in those patches. And if most of the objects found are in those patches, they're going to appear clustered there, whether or not any planet is actually organizing them. It's the same logic as a net with big holes. What you catch tells you about the fish in the area, but it also tells you about where you threw the net. Batigian and Brown knew this was a problem before anyone pointed it out to them. They knew the observational bias argument was the strongest objection to their work, and they spent considerable effort trying to address it. What they did was build a statistical model of where surveys had actually been looking, how deep those surveys went, and what population of objects they were realistically capable of detecting. They then asked whether a uniform, unclustered distribution of extreme trans-Neptunian objects could produce the apparent clustering they were seeing, given the biases in where those objects had been found. The answer was that it couldn't. The bias was real, but it was not strong enough to produce the degree of clustering in the actual data. Were they right? That depends on who you ask. Some researchers accepted the bias correction and moved forward. Others argued the bias was harder to model than Batigian and Brown assumed, that the searches were more concentrated than the analysis suggested, that the sample was too small to draw firm conclusions from. Scott Shepard, one of the researchers who helped start the whole conversation in 2014, remained cautious. He believed the clustering was suggestive, but thought the sample needed to be larger before anyone could make strong statistical claims. His position wasn't that the planet doesn't exist. It was that the evidence wasn't yet ironclad. As more objects have been discovered, the picture has continued to look more consistent with the clustering being real. The total number of objects showing the anomalous behavior has grown past 6, past a dozen, and each new addition either strengthens the pattern or weakens it. So far, the pattern has mostly held. What makes the clustering evidence compelling isn't any single number. It's the combination of the probability calculation, the anti-alignment prediction, the multiple independent orbital parameters all pointing the same way, and the fact that the bias corrections, while imperfect, don't seem to make the signal disappear. After correcting for every known source of observational bias they could identify, Batygin and Brown found that the clustering remained statistically significant. Not ironclad proof, but strong enough that explaining it without invoking a massive unseen planet required more special pleading than most researchers were willing to do. The mechanism by which a single unseen planet could herd dozens of small objects into the same orbital orientation has a name that sounds technical but describes something almost elegant. It is called mean motion resonance, and once you understand what it actually does, the idea that one invisible planet could be quietly organizing the outer solar system without anyone noticing for centuries starts to feel less like a science fiction premise and more like a straightforward consequence of how gravity works. Start with something familiar. Think about pushing a child on a swing. The swing has a natural rhythm, a period that is set by the length of the chain and nothing else. If you push at random moments, sometimes you add energy and sometimes you take it away. The swing stays roughly the same. But if you push at exactly the right moment in the cycle, every single time, the energy builds. The swing goes higher. The timing is everything. What you are doing, in the language of orbital mechanics, is driving a resonance. You are not fighting the system. You are working with it at its own frequency. The result is something stable and controlled that no single random push could ever produce. Mean motion resonance between two orbiting bodies works the same way. When two objects orbit the same star and their orbital periods fall into a simple ratio, 2:1, 3:2, 4:9, they complete their orbits in lockstep. They approach each other at regular, predictable intervals, always in the same configuration, always exchanging a small kick of gravitational energy at the same point in their paths. That regularity is what makes resonance different from a random gravitational nudge. The kicks are not scattered across the orbit. They are concentrated, and over millions of years, concentrated kicks in the same direction add up to something enormous. Jupiter's moons are the clearest example in our own solar system. Io, Europa, and Ganymede orbit Jupiter in a 4:2:1 resonance. For every 4 times Io goes around, Europa goes around twice, and Ganymede once. They have been locked in that ratio for billions of years. The resonance is what keeps them there. Saturn's rings show the same physics from the other direction. Where a small moon's orbital period lines up with the period of ring particles, the repeated gravitational kicks clear the particles out. The dark gaps that Cassini photographed so beautifully. The gaps in Saturn's rings are not accidents. They are the fingerprints of resonance, places where the math said the kicks would always push outward. Over time, the particles left. Planet 9 is predicted to do something structurally similar to the distant Kuiper Belt objects, just on a far longer timescale and across a vastly wider region of space. The objects in question have orbital periods of thousands of years. Planet 9, if it exists, has an orbital period somewhere between 10,000 and 20,000 years. The ratios that emerge from those numbers produce resonant configurations where a distant Kuiper Belt object and Planet 9 return to the same relative geometry at regular intervals. Separated by thousands of years between each encounter, but repeating with the same precision every time. Here is what happens when one of those objects falls into resonance with Planet 9. At each close approach, and close here means still enormously distant in human terms, but gravitationally significant, the object receives a small nudge. Because the nudge always arrives at the same point in the orbit, it always pushes in the same direction. Over millions of years, this relentless one-directional pressure slowly rotates the object's orbital orientation. The long axis of the ellipse, the line that runs from the object's closest approach to the Sun all the way out to its farthest point, gradually swings around and locks into a specific alignment relative to Planet 9. The object does not spiral in, it does not fly away. It settles into a configuration where the resonance itself becomes self-reinforcing, where the kicks now work to keep the orbit in place rather than push it further. This is the counterintuitive part. The same mechanism that initially aligns the orbit then acts as a cage. Once the object is in resonance, the gravitational exchange at each encounter pushes back against any perturbation that tries to knock it out of alignment. The resonance is self-correcting. You can think of it like a ball sitting in a bowl. Push it in any direction and the walls push back. Planet 9 does not need to babysit each object individually. The orbital mechanics do the work automatically, without any ongoing intervention, just the same repeating interaction playing out over geological time. What Batagian and Brown found when they ran simulations of this process was that Planet 9, in the orbit they predicted, would naturally produce exactly the clustering that is observed. Objects entering the resonance from various starting configurations would, over hundreds of millions of years, be steered into the anti-aligned orientation that the surveys have actually detected. The clustering is not a snapshot of some brief coincidence. It is the steady-state endpoint of a process that has been running since the early solar system. And this matters because the number of objects that are supposed to be in this pattern is not small. The simulations suggest that over the age of the solar system, Planet 9 could have shepherded a significant fraction of all extreme trans-Neptunian objects into this configuration, not by touching them, not by coming anywhere near them in any meaningful sense, just by existing at the right distance with the right orbital period and letting the mathematics of resonance do the rest. The orbital choreography is not a coincidence of physics. It is physics working exactly as it should. The fact that the distant Kuiper Belt objects fit the predicted resonance pattern so well is one of the strongest arguments that something real is out there doing the shepherding. Mike Brown discovered Sedna in 2003 and immediately knew he had a problem. Not the good kind of problem, where you find something unexpected and the explanation is obvious once you look. The bad kind. The kind where you stare at the numbers, run them again, and realize that what you are looking at should not exist under any version of how the solar system is supposed to work. Sedna was not a mystery waiting for a clever answer. It was a flat contradiction of the standard model, sitting out there in the dark at roughly 76 astronomical units from the Sun, following an orbit so stretched and so distant that at its farthest point it swings out to around 900 astronomical units before slowly, over thousands of years, drifting back in. And here is the thing that broke the model. At its closest approach to the Sun, Sedna still never gets anywhere near Neptune. Its perihelion sits at about 76 astronomical units. Neptune orbits at roughly 30. That gap matters enormously. To understand why, you have to know how normal Kuiper Belt objects get their orbits. The standard picture is straightforward. Neptune is the great sculptor of the outer solar system. Objects that stray too close to it get gravitationally kicked outward into elongated orbits, sometimes extremely elongated ones, stretching hundreds of astronomical units from the Sun. But those kicks work in both directions. The same gravitational interaction that flings an object outward will eventually, over many passes, pull it back. Normal scattered disk objects return to Neptune's neighborhood. They cross Neptune's orbit on the way in and on the way out. Every interaction leaves a trace. Neptune is the mechanism, and the mechanism requires contact. Sedna never makes contact. Its orbit does not cross Neptune's. Neptune cannot have scattered Sedna into its current path because Neptune cannot reach it. Whatever put Sedna where it was not the planet we can see. That is the problem. It is not subtle. It is not a statistical anomaly that shows up only in refined data. It is a fundamental impossibility under the Standard Model, sitting out there at 76 astronomical units, announcing itself every time you run the orbital calculation. So what else could explain it? Astronomers came up with 3 serious possibilities. The first was a close stellar encounter early in the solar system's history. The Sun formed inside a dense stellar nursery, surrounded by thousands of other young stars, before those stars dispersed over tens of millions of years. If one of those stars passed close enough, its gravity could have pulled Kuiper belt objects outward, detaching them from Neptune's influence and depositing them in distant orbits with high perihelia. The math works, roughly. A star passing at around 800 astronomical units could produce objects with Sedna-like orbits. The problem is that such an encounter would need to have happened within the first few 100 million years, and it would need to have been a fairly specific kind of pass. Not impossible, but it requires a piece of early solar system history that no one has directly confirmed. The second idea was even more dramatic. What if Sedna was not originally part of our solar system at all? Some models suggested that the Sun could have captured small bodies from neighboring stars during the crowded early period in the birth cluster. A passing star brings its own Kuiper belt objects into the neighborhood. The Sun's gravity snags a few, and those captured bodies end up in exactly the kinds of detached, high perihelion orbits that Sedna occupies. It is a legitimate mechanism. Several papers worked out the orbital dynamics in reasonable detail, but it is also a difficult idea to test, and it still leaves open the question of why these orbits look the way they do. The third option was quieter, more uncomfortable. What if something is out there right now? Not a star that passed billions of years ago. Not a capture from another system. A massive body, still present, still exerting a gravitational pull on the outer solar system. Something that pushed Sedna out and is still pushing. For years, this idea sat at the edges of the conversation because there was only one Sedna. One object can be a fluke. One object does not prove a pattern. Then, in 2014, Trujillo and Shepard found 2012 VP113. The name is not memorable. The orbit is. This object had a perihelion of around 80 astronomical units, never approaching Neptune, tracing a path through the outer solar system with no connection to any known planet. A second detached object. A second impossibility. The same kind of orbit, the same detachment from Neptune's reach, showing up again in the same general region of the sky. The chance of 2 such objects appearing by coincidence, with no underlying cause, started to look very small. What had been a mystery doubled overnight. This is the part where Batygin and Brown's models become important in a specific way. When they ran simulations of the outer solar system with Planet 9 included, something interesting happened. The planet did not just shepherd the orbital orientations of extreme trans-Neptunian objects over time. It actively produced Sedna-like bodies, standard Kuiper belt objects interacting with Planet 9's gravity through the resonance mechanism described earlier, got slowly pulled away from Neptune's gravitational reach. Their perihelia lifted. Over millions of years, objects that started as ordinary scattered disk members ended up detached, tracing high perihelion orbits with no connection to Neptune. The model generated Sedna-like objects naturally, without any special conditions, as a direct consequence of Planet 9's existence. That is a meaningful result. It does not just explain the clustering of orbital orientations, it explains why these detached objects exist at all. It turns two separate mysteries into one answer, and the answer points the same direction every other piece of evidence points. Sedna was not supposed to exist, and finding a second one in 2014 only made the problem harder. Two objects that cannot be where they are, according to any model that does not include something massive and unseen sitting far out in the dark. One of the tests that distinguishes a real scientific hypothesis from a just-so story is whether it produces unexpected predictions, things nobody asked it to explain, which turn out to be true anyway. When Batajian and Brown published their 2016 paper, the core argument was about clustering. 6 extreme trans-Neptunian objects were bunched together in a way that looked almost impossible by chance, and a massive planet in an anti-aligned orbit could explain the pattern. That was the claim. That was what they set out to prove. But the math did not stop there. When you run a simulation of how Planet 9's gravity works on distant objects over hundreds of millions of years, something unexpected falls out of the equations. A second population of objects should exist, not clustered in the same plane as Planet 9, but tilted almost perpendicular to it, nearly at right angles to the entire flat disk of the solar system. Nobody asked for this prediction. It just appeared. To understand why this happens, you have to think about what Planet 9 is doing to objects over deep time. It is not nudging things gently in one direction. It is running a slow gravitational campaign across geological timescales, pulling orbital orientations into specific configurations through resonance. Most objects get locked into the anti-aligned clustering that started the whole conversation, but some objects, depending on where they start and how their orbits interact with Planet 9's influence, get pushed in a completely different direction. The math shows that their orbital planes get tilted steeper and steeper over millions of years until they are orbiting almost vertically compared to everything else in the solar system. These would be high-inclination objects, strange ones, the kind that, if you found one, you might write off as an oddity from some ancient gravitational encounter and move on. And that is exactly what astronomers had been doing. High-inclination trans-Neptunian objects were known before 2016. They were considered curiosities. There was no unified explanation for why some distant objects followed orbits tilted so steeply out of the solar plane, while most did not. Some researchers had noted them, catalogued them, and essentially filed them away under unexplained phenomena. There were bigger puzzles to work on. Then Batajian and Brown's paper arrived, and the prediction was right there in the appendix. Planet 9 should be producing a population of objects in roughly perpendicular orbits. Here is what those orbits should look like. Here is the range of inclinations to expect. and observers went back through existing survey catalogues with fresh eyes and started checking. What they found was striking. There were already objects in the data that matched the prediction almost exactly. High-inclination extreme trans-Neptunian objects sitting in orbits tilted between roughly 50 and 130 degrees relative to the solar plane, clustered along specific orientations that the Planet 9 model had predicted in advance. Not one object, not two. Several of them, distributed across the sky in a pattern consistent with what the simulation had produced. Objects that had seemed like isolated anomalies were suddenly part of a coherent picture. In the last few years before this writing, observers identified at least 4 objects tracing orbits along one perpendicular line from Neptune, and 1 object along another. These are small numbers, but the point is not the count. The point is the match. These objects were not discovered in order to confirm the prediction. They are already sitting in survey archives, catalogued before the Planet 9 hypothesis existed. The prediction was published, and then someone checked whether reality had already done the experiment. This is how scientific confidence actually builds. It is not about finding more examples of the thing your theory was designed to explain. Any sufficiently flexible model can be tuned to fit its target data. What you cannot fake is a prediction that goes somewhere the theory was not aimed. Planet 9 was proposed to explain orbital clustering in one specific plane. The perpendicular population prediction was a byproduct of the mathematics, not the goal. When a theory wanders into territory, it was never pointed at and still describes what is actually there. That is a different kind of evidence. Think about what it would take for this to be a coincidence. You would need the high-inclination objects to be distributed roughly randomly. You would need the specific orientations Batygin and Brown calculated to have no particular meaning. And you would need all of this to line up with the survey archives by chance. The probability gets uncomfortable quickly. Not impossible, but uncomfortable in exactly the way that makes researchers lean forward in their chairs. There are still legitimate questions. The sample is small. A handful of objects is not a statistical avalanche. Each new discovery of a high-inclination extreme TNO either fits the pattern or introduces a complication, and the community is still working through what the full distribution actually looks like. High-inclination objects are harder to find than low-inclination ones because surveys tend to be concentrated near the solar plane. That bias means the known population is almost certainly incomplete, and the real distribution could look different once a deeper, wider survey fills in the gaps. But the core fact does not go away. Before 2016, nobody knew why certain distant objects followed nearly vertical orbits. After 2016, there was a specific model that said those objects should exist, described roughly where they should be concentrated, and explained the mechanism producing them. The mechanism is the same long-period resonance that drives the clustering. Planet 9 as a gravitational shepherd creates 2 populations at once, one aligned, one perpendicular, and both seem to be real. Observers found the perpendicular objects. They were already in the data, waiting to be recognized for what they were. And that fact alone moved Planet 9 from an interesting speculation to something that looks increasingly like a real prediction about the actual structure of the solar system. The predicted orbit of Planet 9 has been moving around as more data comes in, and tracking how it has changed actually tells you a lot about how the hypothesis has matured. When Batygin and Brown published their original 2016 paper, the numbers were wide. They estimated Planet 9 sat somewhere between 400 and 800 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. Neptune, the outermost known planet, orbits at roughly 30 astronomical units. So even the closest end of that early estimate put Planet 9 more than 13 times farther out than Neptune. The far end put it almost 27 times farther. That is not a tight constraint. That is a search area the size of a continent when you are looking for something the size of a house. The reason the range was so wide comes down to how the orbit gets inferred in the first place. Researchers are not measuring Planet 9 directly. They are working backwards from the motion of small objects it is presumably pushing around. The more extreme trans-Neptunian objects you have well-characterized orbits for, the tighter your model gets. In 2016, the dataset was thin. 6 objects, good enough to identify the clustering pattern, not good enough to pin down the planet's exact position with any precision. Every new object added to the catalogue since then has acted like a new data point tightening the picture. By 2021, the estimate had sharpened considerably. The semi-major axis, which is the average distance across the full length of the orbit, came down to roughly 380 astronomical units, with an uncertainty range that had narrowed significantly compared to the original proposal. That number shifted again shortly after, landing closer to 460 astronomical units. Then, in 2025, with better modeling and more objects in the dataset, researchers pushed it down further to around 290 astronomical units, with an uncertainty of plus or minus about 30 astronomical units. That is a meaningful compression. The search area has gone from a sprawling range spanning hundreds of astronomical units to something researchers can actually start pointing telescopes at systematically. What does an orbit at 290 astronomical units actually look like? Planet 9 is not in a circular orbit. That much has been clear from the beginning. A circular orbit at 290 astronomical units would be strange enough on its own. But the orbit is highly eccentric, stretched out in an elongated ellipse rather than a round loop. That means the planet swings relatively close at one end, its perihelion, and then arcs out to a much farther distance at the other end, its aphelion. Current models put the perihelion somewhere in the range of 300 astronomical units, and the aphelion out past 500 astronomical units, possibly farther. The planet spends most of its time near the far end of that arc, which is part of why it is so hard to find. It moves slowly out there. It reflects almost no sunlight, and it is pointed away from the parts of the sky that most surveys have covered most thoroughly. The orbital period follows from those numbers. At a semi-major axis near 290 astronomical units, Planet 9 would take somewhere between 10,000 and 20,000 years to complete a single orbit around the Sun. To put that in perspective, 10,000 years ago, humans were just beginning to farm. The planet has not completed a single full loop in all of recorded human history. We are watching one frame of a very slow film. The orbital inclination, the angle at which Planet 9's orbit tilts relative to the flat plane of the solar system, adds another layer of complexity to the search. The best current models suggest an inclination of somewhere around 15 to 20 degrees. That is tilted enough to push the planet out of the narrow band of sky where most planetary surveys are concentrated. but not so extreme that it would be invisible to wide-field surveys designed to cover large areas. Now here is the part that matters practically. The 2025 refinement pushing the semi-major axis estimate down toward 290 astronomical units has a direct consequence for detectability. The closer something is, the more sunlight reaches it. Sunlight falls off with the square of the distance. An object at 290 astronomical units receives more than twice as much light as the same object sitting at 460 astronomical units. That makes it brighter in the sky. Not dramatically brighter. We are still talking about an extraordinarily faint object against a field of millions of background stars. But the margin matters when you are building a survey strategy around barely detectable signals. The mass estimate has moved too. The original 2016 paper put Planet 9 at roughly 10 Earth masses. That number has been revised downward. Current estimates lean toward 5 to 6 Earth masses. That puts it firmly in the category researchers call a super-Earth or sub-Neptune, smaller than the original proposal, but still massive enough to explain the gravitational effects on the outer solar system. Whether it is closer in character to a scaled-up rocky planet or a stripped-down ice giant is still an open question. A 2025 study suggested the composition might skew rocky rather than icy, which would affect its reflectivity and therefore how bright it appears. All of these refinements, the shrinking semi-major axis, the updated mass, the tighter inclination range, feed directly into where astronomers point their telescopes next. A hypothesis that can only say somewhere between 400 and 800 astronomical units in some direction is nearly impossible to test in any reasonable timeframe. A hypothesis that says roughly 290 astronomical units, inclined about 15 degrees, currently near a particular region of sky, is a search target. That shift from vague to specific is how a theoretical idea becomes something you can actually go look for. The latest models suggest Planet 9 is somewhat closer and somewhat smaller than originally thought, which sounds like bad news for a dramatic discovery, but is actually good news for finding it. A closer, still massive planet means that if the right survey points at the right piece of sky at the right moment, the discovery could happen very soon. The question every skeptic asks first is the obvious one. If there is a planet out there, why hasn't anyone seen it? It is a fair question. We have mapped craters on Mars, photographed storms on Jupiter's moons, and tracked asteroids no bigger than a house. The idea that an entire planet, something 5 or 6 times the mass of Earth, could be sitting in our own solar system without anyone noticing seems almost absurd. But the answer comes down to a few brutal physical realities, and once you understand them, the mystery of why we haven't found it starts to feel less like a failure and more like an inevitability. Start with light. Everything we see in the sky, from distant galaxies to the faint smudge of a comet, is visible because it reflects or emits light that reaches our instruments. Planet 9 reflects sunlight, just like every other planet. The problem is how much sunlight reaches it in the first place. Light from the sun weakens with distance, following what physicists call the inverse square law. Double the distance, reduce the brightness by a factor of 4. At Neptune, roughly 30 astronomical units from the Sun, sunlight is already about 900 times fainter than what hits Earth. Planet 9 is predicted to sit somewhere between 300 and 500 astronomical units out. At 500 astronomical units, sunlight arrives at roughly 1/1,000,000th the intensity we experience here. The planet reflects that already feeble light back toward us, and by the time those photons travel hundreds of astronomical units back to Earth, the signal is extraordinarily small. Planet 9 would be so dim that even our most sensitive instruments struggle to pick it out against the background darkness of space. Then there is the sky itself. People underestimate how enormous it is. The whole celestial sphere covers roughly 41,000 square degrees. Planet 9's predicted orbit, based on the latest models, sweeps across a significant fraction of that area, and pinpointing exactly where along that orbit the planet sits right now is still an open problem. Surveys don't just point at one place and stare. They work in strips and patches, accumulating coverage over years. Even the largest modern sky surveys have covered the full sky only a handful of times, and most of those sweeps were not deep enough or sensitive enough to detect something as faint as Planet 9 at the distances being discussed. WISE is a good example. The Wide Field Infrared Survey Explorer was launched in 2009 and mapped the entire sky in infrared light, exactly the kind of observation you would want for detecting a cold, dark, distant world. Astronomers searched its data specifically for Planet 9 candidates. They found nothing that held up. But WISE was optimized for a different kind of science, detecting warm objects like brown dwarfs and nearby stars. Its sensitivity at the wavelengths and distances relevant to Planet 9 was limited, not ruled out, just not found. Pan-STARRS, a Hawaii-based optical survey that has imaged huge portions of the sky repeatedly over the past decade, also came up empty. Again, not because the planet isn't there, but because optical surveys looking in visible light face the same fundamental problem. A planet reflecting 1/1,000,000th of already weak sunlight produces almost no signal at visible wavelengths. These were serious, rigorous searches. They just weren't quite the right tool at the right depth. Here is the specific challenge that makes this search so technically brutal. Planet 9, if it exists, would appear in a single image as a point of light. That is it. No disk, no fuzzy glow, no distinguishing feature. Just a dot, identical in appearance to the billions of stars and galaxies captured in any wide-field survey image. There is no way to identify it from a single observation. The only way to know you are looking at a planet rather than a star is to see it move. Stars are so far away that they appear fixed in the sky over any human timescale. A planet, even a very distant and slow-moving one, drifts visibly against the stellar background if you compare observations taken months or years apart. But Planet 9 moves slowly. At 500 astronomical units, tracing an orbit that takes somewhere between 10,000 and 20,000 years to complete, the planet barely crawls across the sky from our perspective. In a single year, it would shift by roughly a fraction of a degree, detectable, but only if you know where to look and have images taken at the right spacing to catch that tiny drift. Running that kind of comparison automatically across billions of objects in archived survey data is a genuinely hard computational problem. Most surveys weren't designed to do it. What this means in practice is that the relevant archived data is enormous and still only partially searched in the systematic way needed to catch slow-moving, faint objects. Survey images pile up over years. Each one contains millions of sources. Matching the same patch of sky across observations taken months or years apart, filtering out artifacts, handling gaps in coverage, and then flagging anything that has shifted by the tiny amount expected for a 500 astronomical unit object. That is the work, and it is painstaking. Some of it has been done, most of it has not. There is also the coverage problem to consider honestly. The parts of sky that have been searched most deeply are not uniformly distributed. Some regions have been imaged many times. Others, particularly in the southern hemisphere and in areas obscured by the dense star fields near the galactic plane, have sparse coverage or none at all. Planet 9's predicted orbital path crosses some of those poorly surveyed regions. The absence of a detection in well-covered sky doesn't tell you much about what might be sitting in the gaps. It is genuinely possible that Planet 9 has already appeared in existing survey images multiple times without being recognized. A faint moving dot dismissed as noise, or simply unexamined, because no one knew to compare two images taken years apart at the right coordinates. In 2025, a team of researchers searching through archival infrared survey data announced they had found something. Not a planet, not a confirmed discovery. Something. A faint point of infrared light sitting in two different positions in two different surveys taken 23 years apart. The object had moved, and the distance it covered in those 23 years was exactly what you would expect from Planet 9 moving along its predicted orbit. That is not nothing. That is, in fact, the most promising lead the search has ever produced. Here is what the data actually shows. In 1983, a space telescope called IRAS, the Infrared Astronomical Satellite, swept the sky in infrared wavelengths and catalogued hundreds of millions of objects. It was the first all-sky infrared survey ever completed, and the images have been sitting in archives ever since. Decades later, a Japanese satellite called Akari conducted its own infrared survey of the same sky. When researchers laid the two datasets side by side and looked carefully at the region where Planet 9 is predicted to be, they found something odd. A faint source appears in the IRAS data at one position. That same source does not appear in the Akari data at that position. But roughly 47 arc-minutes away, a small but measurable shift against the background stars, there is an object in the Akari images that was not there in IRAS. The two detections are separated by 23 years and about 47 arc-minutes of sky. That angular movement matches the expected drift of a planet sitting somewhere around 700 astronomical units from the Sun, tracing a slow arc across the background field of distant stars. 700 astronomical units is farther out than the orbital models most researchers have been working with recently. The 2025 refinements pushed Planet 9's likely location closer, somewhere between 290 and 460 astronomical units. An object at 700 astronomical units would be even slower moving, even colder, even dimmer than those estimates suggest. But orbital models carry real uncertainty, and the predictions are ranges, not exact values. A 700 astronomical units detection would be on the outer edge of those ranges, but not outside the realm of what the hypothesis actually allows. The object, if it is real, would be large. The infrared brightness suggests something with a mass greater than Neptune. That fits. Planet 9 was never supposed to be small. 5 to 10 Earth masses, roughly Neptune class in size. That is the target range. An object detectable in the IRAS data at that distance would have to be emitting faint heat of its own. a slow thermal glow from a world that formed billions of years ago and has been cooling in the dark ever since. At 700 astronomical units from the Sun, there is almost no solar heating to speak of. The planet's own internal warmth is essentially all it has left. So why isn't this a discovery? Because 2 data points do not make an orbit. You need a trajectory. You need to see the object in at least 3 positions, ideally more, to calculate where it has been and where it is going. IRAS and Akari give 2 positions, 23 years apart. That is a starting direction. It is not a confirmed path. The object could theoretically be something closer and faster that happened to land in those 2 positions by coincidence. The probability of that is low, but it is not 0. Before anyone can say this is Planet 9, the object needs to be found in a 3rd dataset, preferably a modern one with enough depth and resolution to pin down its location precisely. Then the orbit can be calculated. Then the claim can be made. The researchers who published the candidate were careful about all of this. They described exactly what they had found, exactly why it was interesting, and exactly what would be needed to confirm it. That kind of precision matters. The history of Planet 9 claims, and really the history of trans-Neptunian planet claims going back over a century, is littered with detections that did not survive scrutiny. Being careful is not timidity. It is the whole point. The reaction from the broader Planet 9 community was what you might expect from people who have been hunting something for a decade and suddenly have the best lead they have ever seen. Cautious, genuinely excited, careful about what the data does and does not say. Mike Brown called it interesting. Konstantin Batygin acknowledged the candidate, but noted that recovery in a 3rd observation is the essential next step. The phrasing from most researchers was some version of, "This is promising, and we need more data." And this is exactly the kind of thing that could turn into a real discovery, or could turn into another false alarm. And right now, we cannot tell which. What makes this particular candidate harder to resolve quickly is the age of the source data. IRAS observed in 1983. Akari's relevant survey was conducted in the mid-2000s. Neither instrument exists in a form that can take new observations. The follow-up has to come from completely different telescopes, aimed at a specific patch of sky, going deep enough in infrared wavelengths to pick up a faint, cold, distant object that most surveys were never designed to detect. Some of that follow-up is already underway. Whether it produces a recovery or a non-detection, the answer will come from painstaking work, comparing new deep images against the predicted position, looking for a faint source that has crept a little further along its arc since the last time anyone looked. There is also the question of what a non-detection would mean. If the object cannot be found in current imaging at the predicted position, that does not automatically mean the 2025 candidate was wrong. It might mean the orbital estimate is off. It might mean the object is fainter than expected. It might mean the follow-up surveys were not deep enough. This is the frustrating reality of hunting something at the edge of the solar system. Absence of detection is not the same as proof of absence. But a positive recovery would be unambiguous. You find it moving, you calculate the orbit, you check whether it matches the Planet 9 prediction. That is the moment everything changes. Until the object is recovered in a 3rd independent observation and an actual orbit can be calculated, the 2025 candidate sits where most things in science sit before they become discoveries, in the space between a compelling lead and a confirmed result. which is a genuinely uncomfortable place to be. In late 2025, the most powerful survey telescope ever built began scanning the southern sky from a mountaintop in Chile. The timing was not accidental. The Planet 9 search had reached the point where the next step required an instrument that did not yet exist, and then suddenly it did. The Vera C. Rubin Observatory sits at an elevation of nearly 2,700 meters on Cerro Pachón, a peak in the Chilean Andes chosen specifically for its stable atmosphere and exceptional darkness. What it does is straightforward in concept and almost absurd in scale. Every few nights, it photographs the entire southern sky. Then it does it again, then again. Over 10 years, it will image roughly 10 billion individual objects, and its computers will compare every new image against the archive, flagging anything that has moved. That last part is the whole game. Finding Planet 9 is not a matter of pointing a telescope at one location and waiting for something to appear. The planet, if it exists, would look like a point of light indistinguishable from millions of background stars at first glance. Stars don't move, at least not perceptibly on human timescales. A planet does. Catch the same piece of sky twice, separated by months, and a planet will have shifted position. Catch it a third time, and you have a trajectory. At Planet 9's predicted distance of somewhere between 300 and 600 astronomical units, that motion is extremely slow. We're talking about a world moving at a pace that would take it 10 to 20,000 years just to complete one full lap around the Sun. But slow is not the same as undetectable. The Rubin Observatory's 10-year baseline is long enough to watch it creep. The numbers behind the telescope are worth sitting with for a moment. Its primary mirror is 8.4 meters across. Its camera, called LSST CAM, is the largest digital camera ever built for astronomy, collecting images across a 3.2 billion pixel detector. Each single exposure covers an area of sky roughly 50 times larger than the full moon. The system can scan the entire accessible southern sky every 3 to 4 nights. No telescope with this combination of depth, speed, and coverage has ever existed. Previous surveys like Pan-STARRS and WISE had pieces of what was needed. Neither had all of it at once. The Rubin Observatory has all of it. Mike Brown has been asked many times what instrument he would build if the goal was specifically to find Planet 9. His answer is always the same. He would build the Rubin Observatory, not a variation of it, not something inspired by it. Exactly that telescope. It is, in his framing, the perfect machine for this particular problem. Not because it was designed with Planet 9 in mind, but because the requirements for conducting the deepest, most comprehensive survey of the time-varying southern sky happen to align almost perfectly with what the Planet 9 search demands. The fact that it exists and is operational right now is, depending on how you look at it, either very good luck or the inevitable result of planetary science reaching the point where this kind of instrument was necessary. Here is how the detection would actually work. The Rubin Observatory's software pipeline, running continuously as new images come in, subtracts each fresh exposure from the stored archive. Anything that has stayed in the same position drops out of the comparison. Anything that has moved stays in. The system then catalogues the moving objects and attempts to link detections across multiple nights into coherent orbital tracks. For known populations like asteroids and comets, this is routine. For something at Planet 9's distance, the motion between exposures taken a few nights apart would be tiny, smaller than many expected signals. But over months and years, the accumulated drift becomes unambiguous. The pipeline is designed specifically to find this kind of slow, faint, distant motion. There is a practical constraint worth mentioning. The Rubin Observatory surveys the southern sky, not the whole sky. Planet Nine's predicted orbit does not confine it to the southern hemisphere, and current models place it somewhere in a broad arc that spans both hemispheres. If Planet 9 happens to be sitting in the northern portion of its orbit right now, the Rubin Observatory will not find it directly. What it will do is eliminate the southern portion of the predicted parameter space with a thoroughness that no previous survey has approached. That alone would reshape the search significantly. A non-detection in the southern sky after 10 years of deep coverage would push the orbital models toward northern solutions and tell northern sky observatories exactly where to concentrate. But the optimistic reading of the timeline is more exciting. Brown and Battigan's most recent orbital estimates in 2025 placed Planet 9 at roughly 290 to 460 astronomical units, somewhat closer than earlier predictions had suggested. Closer means brighter. Brighter means the Rubin Observatory has a better chance of catching it in fewer years rather than more. Some researchers think the detection, if it happens, could come early in the survey window rather than at the end. The telescope has been running for months now. The data is accumulating. The comparison pipeline is running every night. What makes this moment different from every previous phase of the Planet 9 search is that the waiting is no longer passive. Earlier, researchers could only analyze the objects already known and run orbital simulations. Now, there is an active machine specifically configured to catch the thing they have been looking for. Each night, the Rubin Observatory runs, adds another layer of data to the archive. Each new comparison narrows the space where Planet 9 can hide. The search has a clock on it now, and the clock is running. Brown's prediction is specific. If something starts moving across the survey images at around 500 to 600 astronomical units from the Sun, following the predicted orbital path, it will be Planet 9. And the Rubin Observatory is essentially built to catch exactly that kind of slow, faint, distant motion. Not everyone is convinced. The Vera Rubin Observatory may be perfectly positioned to find Planet 9, but a meaningful portion of the scientific community is not yet willing to accept that there is something out there to find. These are not fringe voices. They are working astronomers with serious objections. Their arguments deserve the same attention as the evidence on the other side. The loudest challenge to the Planet 9 hypothesis is not about the planet itself. It is about the data being used to justify it. Samantha Lawler, an astronomer at the University of Regina, has argued that the apparent clustering of extreme trans-Neptunian objects is not a real signal. It is a ghost. When astronomers go looking for faint, distant objects in the outer solar system, they do not scan the entire sky equally. Surveys concentrate on certain regions. Some parts of the sky get studied again and again. Others go almost completely unexamined. If your catalogue of known extreme TNOs is drawn primarily from the regions where telescopes have pointed most often, the objects in that catalogue will cluster in those regions almost automatically, not because something is pulling them there, because nobody looked anywhere else. This is observational bias. It is a genuine problem for any argument built on the positions of a small, carefully selected sample of objects. Lawler and her colleagues have run simulations of this effect. They modeled what the known distribution of extreme TNOs would look like if the actual underlying population were spread randomly across the sky. But surveys had only covered certain portions of it. The result looked remarkably similar to the clustering that Batygin and Brown pointed to as evidence for Planet 9. If Lawler is right, the solar system's distant edge may be perfectly ordinary. The apparent pattern is a systematic artifact of incomplete data. This is a hard argument to dismiss. The sample of known extreme trans-Neptunian objects is small. Depending on how you define the category, you are talking about somewhere between a dozen and a few dozen objects. Statisticians will tell you that drawing strong conclusions from a sample that size is risky, even under ideal conditions. When the sample itself is collected through an inherently biased process, those conclusions get shakier still. Batygin and Brown have pushed back on this. They have argued that their analysis accounts for known observational biases, that the clustering persists even when they correct for the regions of sky that have been searched most heavily. The probability of the observed alignment occurring by chance after correction. They estimate at somewhere between roughly 1% and a fraction of a percent. Those are not certainty level numbers, but they are not nothing. Where you fall on this argument depends significantly on how much you trust the bias corrections. That is a judgment call that reasonable scientists are making differently. Then there are the alternative explanations that do not involve a planet at all. One class of models invokes dark matter. The idea is that the gravitational influence attributed to Planet 9 might instead be coming from a concentration of dark matter somewhere in the outer solar system, or from the overall large-scale distribution of dark matter in the galaxy, affecting the orbits of very distant objects. Most researchers find this explanation more complicated than it needs to be. The specific predictions it makes are harder to test. But it is a legitimate scientific position that cannot simply be ruled out. Modified gravity is another alternative. Some researchers have proposed that our understanding of how gravity works at extremely large scales may be incomplete. That the anomalous orbits of distant Kuiper Belt objects are a signature of that incompleteness rather than evidence of a hidden mass. These are serious theoretical proposals, not idle speculation, though most planetary scientists consider them less economical than the Planet 9 hypothesis. Scott Shepherd sits in a different category from the outright skeptics. He was one of the original researchers who noticed the clustering problem. He co-authored the 2014 paper with Trujillo that first raised the alarm. He is not arguing that the signal is definitely fake. He is arguing that the statistics are not yet strong enough to say it is definitely real. His position is essentially that the current sample size cannot carry the weight being placed on it. More extreme trans-Neptunian objects need to be found, and their orbits need to be characterized before the clustering argument becomes truly compelling. The statistical case for Planet 9, in his view, is not closed. It is open, and it will remain open until the data set is substantially larger. This matters because Shepherd knows the data better than almost anyone. He has spent years surveying the outer solar system. When he says the evidence is not sufficient, he is not speaking from ignorance of what the evidence says. He is speaking from a deep familiarity with how fragile the sample still is. The community as a whole reflects this spread of positions. Brown describes himself as extraordinarily confident. Batygin has said that unlike every previous Planet X claim, this hypothesis comes with a specific, testable prediction. Others are more measured. A few are genuinely skeptical in the Lawler sense, believing the whole pattern dissolves once you account properly for where the surveys have pointed. There is no consensus here in any useful meaning of the word. What makes this uncomfortable is that both sides are using the same underlying data set and reaching fundamentally different conclusions about what it means. That is a sign that the data set is not yet good enough to settle the argument. That is precisely what Shepard has been saying. More surveys, more objects, better bias corrections. An independent detection from a telescope like the Rubin Observatory. That is what it will take to move from a contested claim to a resolved one. The honest state of the field is that if you walked into a room of 20 planetary scientists and asked for a show of hands, you would get a spread of answers. The researchers who think Planet 9 probably exists are not uniformly confident. The ones who doubt it are not uniformly dismissive. It is exactly the kind of contested, leave question that makes planetary science worth following right now. In 2025, researchers announced a new object in the outer solar system, and it immediately made things more complicated. The object has a name that only an astronomer could love: 2017 OF201. It's roughly 700 kilometers across, which puts it in the range of a dwarf planet candidate. That's about the distance from New York to Chicago, end to end, rolled into a ball of ice and rock sitting billions of miles from the Sun. By any normal measure, it's a small thing, but its orbit is not small at all. The path this object traces around the Sun is one of the most elongated ever recorded for a body this size. It swings out to enormous distances, far beyond Neptune, far beyond the bulk of the Kuiper Belt, into the same cold territory where Planet 9 is predicted to roam. When the team first announced it, the natural reaction from the Planet 9 community was something close to excitement. Here was another object on an extreme orbit that conventional solar system physics struggles to explain. Something had to push it out there. Something had to give it that elongated path. Planet 9 was the obvious candidate. So far, so good. Then the modeling started. When researchers ran the numbers on 2017 OF201 in detail, a problem surfaced. The clustering that sits at the heart of the Planet 9 hypothesis is not just about objects having extreme orbits. It's about those extreme orbits all pointing in roughly the same direction. The argument of perihelion, the longitude of ascending node, the orientation of the orbital plane, these parameters cluster together among the known extreme trans-Neptunian objects in a way that screams gravitational influence from a single massive source. That clustering is the evidence. That's what the whole case rests on. And 2017 OF201 did not cluster with the others. Its orbit sat outside the predicted pattern. Not wildly outside, not in some completely different region of parameter space, but outside enough to notice. Outside enough to create a real scientific tension. What does that actually mean? There are two ways to read it, and they point in opposite different directions. The first reading is that 2017 OF201 supports the Planet 9 picture. The hypothesis predicts that a massive outer planet would scatter objects across a range of extreme orbits over millions of years. Not every object gets nudged into the same clustered configuration. Some get pulled into the clustering, Some get pushed into perpendicular orbits, and some end up in less ordered paths that still reflect the chaotic gravitational history of the outer solar system. Under this reading, 2017 OF201 is exactly the kind of outlier you'd expect. Its unusual orbit is consistent with the general influence of a large unseen planet, even if it doesn't contribute to the specific clustering signal. The second reading is less comfortable for the hypothesis. If Planet 9 is real and its gravity is shepherding distant objects into coherent orbital families, then why is this object not part of the family? Every non-conforming object is a data point that doesn't fit the model. One non-conforming object is easy to dismiss, but the concern is what happens as more surveys come in and more objects are discovered. If the outer solar system turns out to be full of extreme TNOs that don't cluster, the statistical case weakens. The researchers behind the 2017 OF201 paper were careful. They didn't claim the discovery broke Planet 9. They said more data is needed. That phrase appears constantly in this field, and it is not a deflection. It is a genuine statement about where the science is. Here's the underlying issue. The total number of known extreme trans-Neptunian objects is still remarkably small. Astronomers are making a statistical argument about the structure of a vast, dark region of space based on a sample that most statisticians would call uncomfortably thin. Adding one object that doesn't fit the pattern doesn't destroy the statistics, but it does shift them slightly in the wrong direction. And it raises a question that the skeptics have been asking from the beginning. Is the clustering signal in the existing sample real, or is it a reflection of where the surveys happen to look? What made 2017 OF201 particularly interesting was the question of how it got to where it is. Its highly elliptical orbit is not something that forms easily from standard solar system dynamics. Something gave it that path. The researchers noted that Planet 9 could explain it, but so could a close stellar encounter early in the solar system's history, or dynamics that don't require any undiscovered planet at all. The orbit, taken alone, doesn't confirm anything. It's consistent with several scenarios at once. That ambiguity is exhausting in the best possible way, because it means the outer solar system is still generating genuine puzzles faster than existing models can resolve them. The Vera Rubin Observatory is expected to find dozens, possibly hundreds, of new extreme trans-Neptunian objects over the next decade. Each one will either strengthen the clustering signal or dilute it. 2017 OF201 was a preview of what that process is going to feel like. A new object announced. The community examines the orbit. The orbit doesn't behave exactly as predicted, and everyone updates their confidence levels slightly while agreeing that the question is still open. The outer solar system has a way of producing exactly the kind of ambiguous evidence that keeps a question open just when it seems like it might be closing. And 2017 OF201 was a perfect example of that. If Planet 9 is real, the next question is obvious. Where did it come from? This is not a simple question. An object 5 or 6 times the mass of Earth, sitting somewhere between 300 and 500 astronomical units from the Sun. On an orbit so elongated, it takes 10,000 to 20,000 years to complete a single loop. That is not where planets are supposed to end up. Normal planet formation does not produce this. Something had to put it there. The leading candidates for how that happened are genuinely different from each other in ways that matter. The theory that Batygin and Brown consider most plausible starts about 4.5 billion years ago, in the first few million years of the solar system's existence. The early solar system was nothing like the orderly arrangement we see today. It was a chaotic, dense environment, a disk of gas, dust, rocky debris swirling around a young sun, with planetary embryos forming and colliding and being flung around by gravitational interactions that played out over millions of years. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, were not sitting where they are now. They were closer in, and they were moving. In this picture, Planet 9 started out as the core of what might have become a fifth giant planet. It was growing in the inner part of the outer disk, accumulating mass, heading toward the threshold where it would have started pulling in hydrogen and helium gas and becoming something like Jupiter. It never got there. Before it could cross that threshold, it wandered too close to one of the giants, most likely Jupiter, possibly Saturn. What followed was a gravitational slingshot. The planet's close approach gave Jupiter or Saturn a tiny nudge inward, while flinging the smaller body outward at enormous speed. One encounter, one pass, and a planet-sized object that had been forming in a relatively normal part of the solar system was suddenly launched into a wildly elongated orbit that carried it far beyond anything we would call the solar system today. At this point, the ejected core would have been on an orbit that carried it almost all the way out of the solar system entirely. Its aphelion, the farthest point of its orbit, would have been extraordinarily distant, possibly thousands of astronomical units from the Sun, but it didn't escape. And this is where the story gets interesting. The early Sun was not alone. It formed inside a stellar nursery, a dense cluster of young stars, all born from the same collapsing cloud of gas. Hundreds of stars packed into a relatively small region of space, all moving around each other, all exerting gravitational influences on everything nearby. The gravity of those passing stars, combined with drag from the leftover gas of the solar nebula, slowly worked on Planet 9's orbit. Each close stellar pass nudged the orbit slightly. The gas drag pulled energy out of the most extreme part of the trajectory. Over millions of years, this gradually raised the closest point of the orbit, the perihelion, and reduced the farthest point. What started as a nearly escape velocity trajectory slowly settled into something more stable. By the time the Sun's birth cluster dispersed, Planet 9 was locked into a distant but permanent orbit around our star. The odds of this scenario playing out exactly right have been estimated at a few percent. That sounds low, but a few percent is not zero. Over the violent, chaotic timescales of early planetary formation, a few percent is actually a reasonable outcome. The solar system built 4 giant planets and had extra material left over. Something plausibly could have started forming a 5th. There are other theories. One is that Planet 9 did not form in our solar system at all. The Sun's birth cluster was crowded enough that 2 young stars could have passed within gravitational capture range of each other. In this scenario, Planet 9 was originally orbiting a different star. During a close encounter, the gravitational tug-of-war between the 2 stars pulled Planet 9 free from its original host and left it bound to the Sun instead. Capture is actually a known mechanism. We think the outer Oort cloud may contain objects that were gravitationally borrowed from neighboring stars during exactly this kind of early cluster interaction. Whether a planet-sized object could survive capture in a stable orbit is a more complicated question, but the physics does not rule it out. A third possibility is that Planet 9 formed where it currently lives, or somewhere close to it. The outer disk of the early solar system extended a long way out, and there was material available. The problem with in-place formation at extreme distances is that the material in the outer disk would have been spread too thinly to efficiently accumulate into a planet-sized object in any reasonable time frame. The disk was too sparse, the collision rates too low, the formation window too short. Most researchers find this scenario the least convincing of the three, though it is not impossible if there was a local concentration of material driven by some disk instability. The rogue planet capture scenario is a fourth option. Planet 9 as a free-floating world, ejected from some other star system entirely, drifting through interstellar space until the sun's gravity caught it at just the right moment. The window for this kind of capture is extremely narrow. It requires a very specific geometry, a very specific relative velocity. The probability is low enough that most researchers do not treat it as a serious front-runner, though it cannot be fully dismissed. What most researchers keep coming back to is the ejection story. It fits the predicted orbital characteristics better than the alternatives. It is consistent with what the NEISS model tells us about the early solar system's dynamical history. It requires no exotic physics, no unusual stellar encounters, no improbable capture geometry. Just a young solar system doing what young solar systems apparently do, throwing pieces of itself into the dark. Whatever mechanism put Planet 9 in its current orbit, the solar system's early history was violent enough that a few % probability is not a long shot. It is the kind of thing that, given enough time and enough gravitational encounters, you would expect to happen at least once. If Planet 9 is out there, it is nothing like any planet that has ever had a name. Not like Earth, not like Neptune, not like anything in the lineup of 8 worlds most people learned in school. It belongs to a category that astronomers have named, but our solar system, until now, has never clearly displayed. 5 to 6 times the mass of Earth. That puts it in a range researchers call a super-Earth or sub-Neptune, and it is worth pausing on what that actually means, because the name is doing a lot of work. A super-Earth is not just a bigger version of our planet. At 5 or 6 Earth masses, the gravity pulling on the surface would be significantly stronger. The internal pressure at the core would be far beyond anything Earth experiences. The planet would be a fundamentally different kind of object, sitting in a size class that turns out to be the most common type of planet in the galaxy. We just don't have one nearby to study. What does the interior look like? That depends on which model you trust, and the models have shifted recently. The earlier picture was something close to a mini Neptune, a dense rocky core buried under a thick shell of water and ice, possibly capped by a deep hydrogen-helium atmosphere. Something in the same family as Uranus or Neptune, just smaller. More recent work has pushed back on that. Some researchers now think Planet 9's composition skews rocky, more like a massive terrestrial planet than an icy giant. The distinction matters for detection, because a rockier planet reflects light differently than an icy one, and the predicted brightness used by search teams is built on assumptions about what the surface is actually made of. If those assumptions are wrong, the planet could be dimmer than expected, or brighter. Right now, nobody knows. What is not in question is the temperature. At 500 astronomical units from the Sun, Planet 9 would be extraordinarily cold. the kind of cold that makes the outer planets look tropical by comparison. Neptune, sitting at about 30 astronomical units, already reaches surface temperatures around -200 degrees Celsius. Planet 9 is more than 15 times farther out. At that distance, the Sun's heat is essentially irrelevant. Surface temperatures would sit close to absolute zero, somewhere around -220 to -230 degrees Celsius, possibly colder. There is no process delivering meaningful warmth from outside. Any heat coming from the planet itself would be leftover energy from its formation, slowly leaking out over billions of years. The planet is, in every practical sense, frozen. The darkness is harder to comprehend than the cold. Sunlight at Planet 9's distance is 1/millionth as bright as it is here on Earth. Not 1%, not 1,000th, 1/millionth. On Earth, on a clear day, sunlight is roughly 1,300 watts per square meter. At Planet 9, that number drops to something in the range of 1,000th of a watt. A single household candle produces more light than the Sun delivers to Planet 9's surface. This is why the planet is so difficult to detect. It does not glow on its own and barely reflects anything. From Earth, it would appear as an extraordinarily faint point of light, dimmer than thousands of objects we have already catalogued, indistinguishable from background stars unless you catch it moving across the sky over months or years. Now imagine standing there, not in any practical sense, just as a thought experiment. You are on the surface of Planet 9, or whatever passes for a surface, and you look up. The sky is black, completely black. There are no nearby planets catching the sun's light, no moon overhead, nothing bright enough to illuminate the ground beneath your feet. The stars are there, the same stars visible from Earth, but they shed nothing useful. Then you find the sun. It is not hard to locate because it is the brightest thing in the sky by an enormous margin. Every other star in the night sky seen from Earth tops out at a certain brightness. The sun from Planet 9 would blow past all of them. It would look like an intensely brilliant point of light, far outshining anything else in the sky, the kind of brightness that would be painful to look at directly even from that distance. But it would be a star, not a disk. No warmth, no color spread across the horizon, no sense of a nearby star. Just a hard, blinding point against an otherwise featureless black sky. The surface itself, if the planet has one, would be completely dark. No shadows, no texture visible to human eyes. Whatever geological features exist, craters or ridges or frozen plains of compressed ice and rock, they would be invisible without artificial light. The gravity would pull noticeably harder than Earth's. The atmosphere, if there is one, might be a thin shell of frozen gases clinging to the surface, or nothing at all if the light elements have long since escaped. It would be a world that has been sitting in near-perfect isolation for billions of years, untouched by sunlight, unvisited, unknown. Standing on the surface of Planet 9, if it has a surface in any meaningful sense, the sun would be nothing more than the brightest star in an otherwise pitch-black sky, shedding no warmth, casting no shadows, giving no light that a human eye could use. That is not a problem for scientists. That is the kind of problem that energizes astronomers. Throughout the history of astronomy, observations have repeatedly challenged prevailing models of how planets form and evolve. This is not viewed as a setback, but as an opportunity. When telescopes reveal unexpected features in distant solar systems, or when laboratory analysis of meteorites produces surprising isotopic signatures, researchers recognize these moments as gateways to deeper understanding. The scientific process thrives on such contradictions. They force researchers to examine their assumptions more carefully. They demand more rigorous testing of existing theories. They open new avenues of investigation that might never have been pursued otherwise. Consider how our models of planetary formation have evolved over decades. Early models were relatively simple, proposing that planets coalesced from cosmic dust in straightforward patterns. As observations accumulated, the picture became more complex. Astronomers discovered planetary systems arranged in ways that seemed to violate the assumptions built into older models. Some planets orbited far closer to their stars than theory predicted. Others occupied orbits that crossed the paths of neighboring worlds. These observations sparked intense scientific discussion. Researchers began proposing new mechanisms to explain the data. They suggested that planets could migrate across vast distances. They proposed that gravitational interactions between young planets could reshape orbital configurations dramatically. Each new observation refined the model further. The same principle applies to understanding the early solar system specifically. For many years, scientists relied on a relatively static model of how our system formed. It was assumed that planets settled into their current orbits relatively quickly and remained there. Then came observations of exoplanetary systems that showed far greater dynamism and chaos than anyone had anticipated. These observations, combined with new theoretical work, led to the development of the NICE model and other sophisticated frameworks. These frameworks proposed that the young solar system was far more turbulent than previously imagined. Planets that formed in one region migrated to different orbital zones. Gravitational interactions between multiple planetary bodies created havoc. Some smaller bodies were ejected from the system entirely. Others were scattered into different regions. These revised models explained previously puzzling observations about asteroid and comet distribution patterns. The study of the Moon's formation history provides an excellent illustration of how observations transform understanding. For decades, scientists debated the origin of the Moon. Multiple competing models existed. Some proposed that the Moon had condensed from the same material as Earth, forming as a co-planetary body. Others suggested that Earth had captured the Moon gravitationally from elsewhere in the solar system. Still others argued for different mechanisms entirely. The ambiguity persisted because direct evidence was limited. Then came the Apollo missions. Astronauts brought back hundreds of kilograms of lunar samples. Scientists analyzed these rocks with increasingly sophisticated techniques. The isotopic composition revealed crucial information. The samples showed that the Moon's material was not identical to Earth's material, yet too similar to be a captured body from elsewhere. This observation effectively eliminated several competing models. It pointed toward a different mechanism entirely: a giant impact. The giant impact hypothesis proposed that a Mars-sized body collided with the early Earth. The immense energy from this collision vaporized material from both bodies. Debris from the impact disk coalesced into the Moon. This model could explain the isotopic similarities between Earth and Moon while accounting for their differences. It accounted for the Moon's relatively large size compared to Earth. It explained the Moon's unusual orbital characteristics. When observations of other planetary systems revealed that giant impacts might be relatively common during planetary formation, the hypothesis gained additional credibility. What had once seemed like a radical and controversial idea became the mainstream scientific view, yet even this refined model continues to evolve. New observations raise new questions. Precise measurements of the Moon's composition have revealed subtle variations in different samples. Some concentrations of elements differ slightly from what the original giant impact model predicted. Researchers continue to refine their understanding of the collision's specific characteristics. Did multiple impacts occur rather than one single event? What was the exact size and composition of the impacting body? At what velocity did the collision occur? How much of the Moon's material came from Earth versus the impactor? Scientists cannot yet answer all these questions definitively, but the process of attempting to answer them drives research forward. This pattern repeats throughout astronomical science. Models serve a crucial function. They organize our understanding and make predictions that can be tested. When observations confirm predictions, confidence in the model increases. When observations contradict the model, that contradiction is valuable data. It signals that something important remains misunderstood. It indicates where the model's simplifications or assumptions break down. Rather than viewing this as failure, the scientific community embraces it as progress. The process of questioning and refining models is not separate from science. It is the essence of science. When a confirmed observation breaks a good model, the model gets better. The understanding of what happened 4 billion years ago gets sharper. By most estimates, the wait is not long. Fred Adams at the University of Michigan has looked at the current rate of new trans-Neptunian object discoveries, run the numbers, concluded that somewhere around 2035, the data pool will be large enough to either confirm Planet 9 or force the field to abandon the hypothesis entirely. That is not a long time. Most people reading this will be alive to see that answer arrive. The question is whether the answer will be yes or no, and right now, nobody can tell you. The instrument at the center of that timeline is the Vera C. Rubin Observatory in Chile, which began its survey of the southern sky in 2025. Over the next 10 years, it will image roughly 10 billion objects, comparing new observations against old ones continuously, flagging anything that moves. Planet 9, if it sits in the southern sky at the predicted distance, will move. Slowly, at 500 astronomical units, the orbital speed is glacial from our perspective, but it will move. The Rubin Observatory is precisely the kind of machine designed to catch that kind of faint, slow drift. Mike Brown, the Caltech astronomer who co-authored the original 2016 prediction, has said that if someone handed him unlimited funds and told him to build the perfect Planet 9 telescope, he would build exactly what Rubin already is. That is not a casual endorsement. That is a researcher saying the right tool finally exists. So what happens if the Rubin Observatory finds it? The answer is not simply that a new planet gets added to the list. The discovery would mean the early solar system was far more violent than current formation models describe. It would mean a planetary core formed close to the Sun, was flung outward by a gravitational encounter with Jupiter or Saturn, survived the ejection, has been orbiting in the dark at extreme distance for billions of years. No planet has ever been confirmed to have done this. The NEAS model, which describes how the giant planets migrated early in the solar system's history, would need revision. The broad architecture of our solar system, long assumed to be the product of a relatively orderly formation process, would turn out to be the survivor of something messier. And our solar system, long thought to be unusual for lacking super-Earths and sub-Neptunes, the most common planet type found around other stars, would turn out to have one all along, just hiding. What does non-detection mean? This is where the picture gets more complicated. If the Rubin Observatory completes its survey and finds nothing matching the predicted orbital parameters, that does not prove Planet 9 is absent. The southern sky covers most, but not all of the predicted search zone. A planet in the right orbital configuration could still be sitting in a part of the sky the survey could not reach deeply enough. But non-detection would be significant. It would force researchers back to the clustering evidence and ask harder questions about whether that evidence was ever as strong as it looked. The observational bias problem, the concern that extreme trans-Neptunian objects have been discovered in concentrated patches of sky rather than uniformly. An illusion of clustering would move from a minority objection to the main explanation on the table. The field would have to either find a new explanation for the clustering or accept that the sample was never large enough to draw conclusions from. The clustering itself has been the backbone of the hypothesis since 2016. 6 objects became a dozen. The statistics tightened. The probability of a random arrangement producing what was observed dropped well below 1% by most calculations. But statistics are only as reliable as the sample they are drawn from. The extreme outer solar system is not uniformly surveyed. Every new object discovered carries the potential to either reinforce the pattern or break it. The 2025 discovery of 2023 KQ-14, a Sedna-like object whose perihelion points in the opposite direction from other known sednoids, has already pushed the predicted orbital distance for Planet 9 farther out. The picture keeps shifting. That is not a weakness in the hypothesis. That is how science works when the data is still coming in. The 2025 infrared candidate, the faint source that appeared in one position in the 1983 IRAS data and a shifted position in later Akari imaging, sits in the background of all of this like an unresolved note. The movement is consistent with Planet 9 at roughly 700 astronomical units. The signal is real. But one recovery in archival data does not make a confirmed orbit. A confirmed orbit is what the field requires before anything gets announced as a discovery. Astronomers are currently trying to locate the object in more recent survey images. If they find it, and if the trajectory matches, the timeline to resolution could compress dramatically. The answer might not take until 2035. It might come sooner. That is the thing about this search that is genuinely unusual compared to most open questions in planetary science. The window is defined. The instrument is running. The orbital models are specific enough to tell observers where to look. The candidate in the archival infrared data is already being chased. At some point in the next decade, the Rubin Observatory's computers will compare 2 images separated by months, identify a point of light that has drifted against the background stars. Either that drift will match a Planet 9 orbit, or it will not. The answer is coming. The question is just which answer it will be. Right now, somewhere in a vast stretch of sky that the surveys have not yet covered deeply enough, there may be a frozen world larger than Earth tracing a slow arc around a sun that barely illuminates it. And either it is there, waiting to be found, or it is not. The solar system is stranger and emptier than we thought. Either answer is going to change something fundamental about the picture we have been building for the last 400 years.